In this video, we are going to talk about eigenvalues and eigenvectors. We are going to work with this equation ax equals lambda x. A is a square matrix. If I rearrange this equation to obtain ax minus lambda x, I'll have equal to 0. X is common to these two terms, so if I bring x out, I'll be having a minus lambda I. I is a unit matrix, then x is outside, and this is equal to 0. Yes, I here is a unit matrix. That is a matrix in which the elements, all elements on the principal diagonal are 1, and all other elements being 0. For x not equal to 0, we are going to obtain this. The determinant of a minus lambda I equal to 0. We call this equation the characteristics equation, this equation I have here. And this determinant at the left hand side is called the characteristics determinant. So we are going to be working with this equation and this. The values of lambda for which this determinant right at the left hand side is equal to 0 are called the eigenvalues, or we call them characteristic values, or we can say latent roots. We now go ahead to determine the eigenvalues and the eigenvectors of this matrix. Let's call the matrix A. So what we'll do first of all is to determine the characteristic equation, which is this. Since this is a 2 by 2 matrix, then the identity matrix or the unit matrix itself will also be a 2 by 2 matrix. So it's what we are saying. The determinant of A minus lambda I equal to 0 is this. Okay, 2, and this minus 4, minus 1, minus 1, which is the matrix A, minus lambda I, lambda in brackets, I is 1, 0, 0, 1. This is a unit matrix, and this is equal to 0. Let's subtract this. These two. Okay, look at it. Lambda times 1 is lambda. 2 minus lambda is 2 minus lambda. Lambda times 0 is 0. Minus 4 minus 0 is minus 4. Lambda times 0 is 0. Minus 1 minus 0 is 0 is minus 1. Lambda times 1 is lambda. Minus 1 minus lambda is minus 1 minus lambda, and this is equal to 0. A short way to determine this characteristic equation is this. Since I is a unit matrix, we can just go straight to determine the determinant of this. Subtract lambda from all the elements on the principal diagonal. 2 and minus 1 are on the principal diagonal, so we just subtract lambda from it, and we'll get this. So we may not always need to go through this step all the time. We can easily subtract the lambda from the numbers on the principal diagonal to obtain the characteristic determinant at the left hand side. So we evaluate this 2 by 2 determinant. Alright, as it is, we multiply these two numbers on the principal diagonal. That's 2 minus lambda times this minus 1 minus lambda, then minus 1 times minus 4 is positive 4, and this is equal to 0. So we expand this. We have 2 times minus 1 is minus 2. 2 times minus lambda is minus 2 lambda. Minus lambda times minus 1 is positive lambda. And minus lambda times minus lambda is plus lambda square. minus 4 equal to 0. This is a quadratic equation we have to solve. We have lambda square, which is this. Minus 2 lambda plus lambda is minus lambda. Minus 2 minus 4 is minus 6, and that's equal to 0. To factorize this, we need two numbers when multiplied to give us the product of 1, which is the coefficient of lambda squared, and minus 6. So when I multiply 1 by minus 6, I'm going to obtain minus 6, right? And the coefficient of lambda here is minus 1. That was minus 1. So two numbers when multiplied to give me minus 6, and when added to give me positive 1. Okay, and the numbers are 2 and minus 3, plus 2 and minus 3. So I'll be writing lambda squared plus 2 lambda minus 3 lambda minus 6 equal to 0. And so if I factorize this, I'll be having lambda into lambda plus 2. Alright, I'm taking the first 2 now. Lambda is common to this first 2, so I'll bring it out. I'll be having lambda left plus 2 left. And here, for this last 2, minus 3 is common. And if I divide minus 3 lambda by minus 3, I'll be having lambda. Minus 6 divided by minus 3, I'll be having positive 2 equal to 0. And solving this equation, we produce lambda equal to minus 2 or lambda equal to 3. Because if lambda plus 2 is set equal to 0, we'll be having lambda equal to minus 2. And if lambda minus 3 is set equal to 0, we'll be having lambda equals positive 3. The values of lambda that we have now are called the eigenvalues. Let's call this lambda 1 and let's call this lambda 2. These are the eigenvalues of that matrix A. So what are the corresponding eigenvectors? This is how to do it. To obtain the eigenvectors, what we'll do is this. We are going to come back here now. To this equation I have here, a minus lambda I times x equal to 0. Here, this x is the eigenvector. This is the matrix A, 2 minus 4 minus 1 minus 1 minus lambda. Okay, let's use the first lambda now, which is minus 2. So we are working with the first lambda, which is minus 2. So let me say for lambda 1 equal to minus 2. So lambda 1, we are using minus 2. Actually, the minus, we affect the minus here to give a plus. Okay, so having plus 2 in brackets. The unit matrix 1 0 0 1. Close it. Multiply by x. X is a column vector or a column matrix. Let's use x1 and x2 as the elements in the matrix equal to 0 0 0. So our job here is to determine this matrix or this vector now, x1 x2. That's what we are going to do now. Okay, we have 2. 2 times 1 is 2, right? So 2 plus 2 is 4. 2 times 0 is 0. Minus 4 plus 0, that's minus 4. Times the column matrix x1, x2 equal to 0. Now, I want to convert this matrix into a system of equations. 4 times x1, that's 4x1. Minus 4 times x2, that's minus 4x2 equal to 0. We are just multiplying the matrix on the left hand side. Minus 1 times x1 is minus x1. 1 times x2 is x2, positive x2. And that's equal to what? 0. This is equation 1 and this is equation 2. Actually, these two equations will produce the same result. If we make, for example, x1 the subject of the formula in the first equation, 4x1 equal to 4x2, right? That's this one I have to cross. So dividing both sides by 4, it means that x1 equals x2. If we do the same thing from this same equation 2, we are going to obtain x1 equals x2. You can try it. So I can make use of any of the equations. Okay, x1 equals x2. x1 equals x2. So to determine the eigenvectors, is what I'm going to do. I will ensure that the sign of x1 here is positive with a coefficient of 1, and the sign of x2 here is positive with a coefficient of 1. Of course, x1 is positive here. x2 is also what? Positive here. So this is also the same thing as saying x1 over 1 and x2 all over 1, right? Because I'll get the same result. The eigenvectors corresponding to this lambda 1 equal to minus 2 is this. We said it is x1, x2, right? What's under x1 here is 1. And what's under x2 is also 1. This is the eigenvector that corresponds to lambda 1 equal to minus 2. Let me determine the eigenvector that corresponds to lambda 2 equal to 3. We are still going to do the same thing that we did here, using this from this equation, a minus lambda I times x equal to 0. Okay, in this case now, lambda is now 3. So we're having the matrix A, okay, is this. That will be 2 minus 4 minus 1 minus 1 minus, okay, lambda 2, which is 3. So we have minus 3 into the unit matrix 1 0 0 1 times the corresponding eigenvector of lambda 2. Okay, that's x1, x2 equal to 0 0 0, right? 3 times 1 is 3. 2 minus 3, that's minus 1. 3 times 0 is 0. Minus 4 minus 0 is minus 4. 3 times 0 is 0 again. Minus 1 minus 0 is minus 1. 3 times 1 is 3. Minus 1 minus 3 is minus 4 into x1, x2. This equals 0 0. Alright. So if we turn this into a system of equations, we are going to obtain minus 1 times x1, that's minus x1, minus 4 times x2, that's minus 4x2 equal to 0. The same thing here, if we multiply this row by this column, that will be minus x1 minus 4x2 equal to 0. Now, from these two equations, I have, if I make x1 the subject, I'll be having minus x1 equal to 4x2, right? So I want to make the coefficient of x1 and x2 to be positive 1, to be 1. Here I'm having minus 1, here I'm having plus 4. See, I can write this side like this. x1 all over minus 1. Do you agree? They are the same thing. This and this, they are the same. And I can write this one like s2 all over 1 all over 4. What I did here is this. I multiplied. See, look at it. I have 4. So if I multiply 4 by the reciprocal of 4, which is 1 over 4, here it is 4 over 1. So if I multiply by the reciprocal, I'm going to obtain 1. To make this coefficient positive 1, divide by the reciprocal of what we have here. Okay, and the reciprocal of what we have here is 1 over 4. Okay, I'm not going to divide this side by 1 over 4. Okay, it's just this side. It's as if nothing has happened. You get it? Because if I simplify this now, x over 2, this one now will give me x2 divided by 1 all over 4, right? So the division will turn to times, and it will be x2 times 4 all over 1. 4 times x2 is 4x2 all over 1, like what we have before. So that's it. So the eigenvector that corresponds to lambda 2 equal to 3 would be this. What is under x1? Minus 1. And what's under x2? 1 all over 4. The simplest eigenvector is this. I'm having a fraction inside. What I'll do is to multiply by 4. Do you know why? It's all over 1. So the LCM of 1 and 4 is 4. If I multiply this by 4, I'll have this. That'll be 4 times this. 4 times minus 1 is minus 4. 4 times 1 over 4, that's 1, of course. So this is the eigenvector that corresponds to lambda 2 equal to 3. So this eigenvalue minus 2 corresponds to this eigenvector, and this eigenvalue 3 corresponds to this eigenvector. All right. Now I'm going to solve this question. I will not go through all these steps I went through. I'll be cutting off some steps. Just watch how I'm going to do it. I want to find the eigenvalues and eigenvectors of the matrix that is here. First of all, remember we have to determine the characteristic equation, and that is it. I told you the characteristic equation is this. This is a minus lambda I equals 0. That's the determinant of this equal to 0. So I'm going straight now. The matrix A is this. So I'll just subtract lambda from minus 6 and 2 to be minus 6. Then I'll be having minus lambda. I'm having 5. This will remain the same. And here I'll be having 2 minus lambda. And this is equal to 0. Let's evaluate the 2 by 2 determinants. This times this minus this times this. Minus 6 minus lambda times 2 minus lambda minus 20, right? This times is 20 equal to 0. So minus 6 times 2, that's minus 12. Minus 6 times minus lambda is plus 6 lambda. Lambda minus lambda times 2 is minus 2 lambda. Okay. Minus lambda times minus lambda is positive lambda squared. Minus 20 equal to 0. And so we have lambda squared. 6 minus 2, that's 4. So we have plus 4 lambda. Minus 12 minus 20 is minus 32. And this is equal to what? To 0. And so we have to factorize this. Two numbers when multiplied to give me 1 times 32. That's, okay, minus 32. That's minus 32. When added to give me 4, positive 4. That should be 8 and 4. But in this case now, the 8 will be carrying a plus. The 4 will be carrying a minus. So I'm having lambda squared plus 8 lambda minus 4 lambda. After all, 8 lambda minus 4 lambda is 4 lambda, right? Minus 32 equal to 0. So this is lambda into lambda plus 8. I'm factorizing now. If I bring out minus 4 from here, I'm having minus 4 into lambda plus 8 equal to 0. So the two of them in bracket are the same. That's lambda plus 8. Then I have lambda minus 4 equal to 0. And this will produce the two eigenvalues, lambda equal to minus 8 and lambda equal to 4. Alright, so let's call this lambda 1 and let's call this one lambda 2. These are the eigenvalues. What are their corresponding eigenvectors? For the first eigenvalue, lambda 1 equal to -8. We are now going back to this equation that says a minus lambda I into x equal to 0. And the matrix for the left hand side is this. A minus lambda I can be easily determined. That's what we have here, the entries we have here. So I can just put that here. -6 minus lambda, 5, 4, 2 minus lambda. This one is a minus lambda I. X, which is the eigenvector, has the entries x1, x2 equal to 0. You can use anything here, x and y, or any other letter, but I'm using x1 and x2. So for lambda 1 equal to -8, I'm going to plug in -8 here. I'll plug in -8 for lambda. So I'll be having -6 minus -8. What's -6 minus -8? That's -6 plus 8. That'll give me 2, right? I'm having 2. Here's the 5. Here's 4. Then 2 minus -8. That's 2 plus 8. And that's 10. Times x1, x2 equal to 0. The 0 vector. So if I convert this to a system of equations, I'll be having 2 times x1 plus 5 times x2 equal to 0. That's 2x1 plus 5x2 equal to 0. 2x1 plus 5x2 equal to 0. We'll come back again. 4 times x1 plus 10 times x2 equal to 0. That's 4x1 plus 10x2 equal to 0. I'll write that down. That's 4x1 plus 10x2 equal to 0. I hope you can see that if you simplify this second equation, you are going to obtain the first equation. Divide everything here by 2. This will be the result. So I want to use the simpler equation, which is equation 1. From equation 1 now, 2x1 equal to -5x2, right? I want to make the coefficient of x1 and x2 to be +1. Okay, here is already a 2. So what I want to do is, like what I did earlier, since I'm having a 2, I'll multiply it by the reciprocal of it to give me 1. So it's simple. What I'll do is this. I'll write x1 divided by the reciprocal of 2, which is 1 over 2, equal to, first of all, I'm having x2 here. There's a minus. Bring the minus out. Then the reciprocal of 5 is 1 all over 5. I hope this is clear. So the eigenvector that corresponds to lambda 1 equal to -8, remember that's what we're doing? Lambda 1 equal to -8 is the vector. What's under x1? 1 over 2. What's under x2? -1 over 5. The simplest eigenvector is this. If I multiply this vector, it has a fraction. So I want to clear off the fraction to write it in the simplest form. If I multiply by 10, why am I using 10? Because the LCM of 2 and 5 is 10. So if I multiply this by 10, I'll be having 10 over 2. And I'll be having -10 all over 5. And what would this be? This would be 5 minus 2. This is the eigenvector that corresponds to the eigenvalue lambda 1 equal to -8. What about the eigenvector that corresponds to lambda 2 equal to 4? Okay, So for lambda 2 equal to 4, I want to do something now. See, I'm working with this. Okay. We got this when we substituted minus 8 for lambda here. This is what we got. So I want to substitute 4 for lambda here. I'll get this. Minus 6 minus 4 as minus 10. So I'm having minus 10. Similarly, this 5 will remain. The 4 will also remain because nothing attached. But here we'll be having 2 minus 4, which is lambda 2, and that will give us minus 2. Okay, so multiply this by the column vector x1, x2 equal to the 0 matrix. Minus 10x1 plus 5x2 equal to 0, of course, and 4x1 minus 2x2 equal to 0. Equation 1, equation 2. This times this plus this times this. This times this plus this times this, which is this. The plus and the minus will intersect to produce a minus. So I can use any of the equation. I'll still get the same result. You can verify it. Let me use equation 1. Okay, let's see. Let's check it out here. Let me verify it so that you can see. Equation 1 is minus 10x1 plus 5x2 equal to 0. If I make x1 its subject, I'll be having minus 10x1 equal to minus 5x2. Divide both sides by minus 10. Five here is 1, 5 here is 2. So I'll be having x1 equal to x2 all over 2. Right? That's what I will be having. So if I do the same thing from equation 2, where it is, we will have 4x1 minus 2x2 equal to 0. So it will now be making x1 its subject. 4x1 equal to 2x2. The minus 2x2 will cross and turn to a positive 2x2. Dividing both sides by 4, x1 is 2x2 all over 4. 2 here is 1, 2 here is 2. So x1 is x2 all over 2. You see that we have the same thing here. So that's why I said any equation can work. So let me use equation 1. So using the first equation, we just determined that x1 is equal to x2 over 2 from either of the equations. So I'm not going to solve anymore. I'll just write x1 equal to x2 over 2. See, from any of the equation, x1 equals x2 all over 2. And I hope you understand this. So what is the eigenvector that corresponds to lambda 2 equal to 4? Is this. I need this to be positive 1. I need this to be positive 1 also. It is already 1 here, plus 1 here. It's already plus 1 here. Under x2 we have 2. Under x1 we have 1. So the eigenvector that corresponds to this eigenvalue is 1, 2. This is under x1. This is under x2. Corresponds to lambda 2 equal to 4, right? And the first one we got, which is this corresponds to lambda 1 equal to minus 8. This is it for eigenvalues and eigenvectors of 2 by 2 matrices. I'll see you in the next video. Keep watching, subscribe, like, and share this video.